अस्सलाम वालेकुम मैम।
वालेकुम सलाम। कौन बोल रहा है?
सोहेब था है।
क्या हाल है सोहेब?
अल्हम्दुलिल्लाह मैम, आप सुनाएं।
फाइन, थैंक यू। हेलो अबीरा।
Good morning, ma'am.
गुड मॉर्निंग, हाउ आर यू?
I'm good, ma'am. How are you?
फाइन, थैंक यू। हेलो सर। Zaresh, are you there?
Hello, ma'am. Yes, ma'am. Good morning, ma'am.
Morning. Hello Cheryl.
Good morning, ma'am.
Good morning. Hello Sohaib. Sohaib, I cannot hear you.
जी जी मैम।
हाँ जी। Okay. Hello Bilal.
Good morning, ma'am.
Good morning. Hello Hamzadar.
Yes, ma'am.
How are you?
Good, ma'am.
कौन रह गया है जिसका नाम नहीं बुलाया मैंने? मुआज, हेलो मुआज।
हेलो मैम।
हेलो उस्मान बाजवा। उस्मान बाजवा, we cannot hear you. Hello Amelia. We cannot hear Amelia as well. Okay. Okay, fine.
Hello. Good morning, ma'am. Sorry, my mic was off and I was speaking.
Good morning. Okay, so what were we studying last time? क्या पढ़ रहे थे हम लोग? Who would like to give us a small recap? कौन बताएगा?
Ma'am, we were having introduction to gravitation, like gravitational waves
Okay, yes, we were talking
and its
about
formula.
Yes, we were talking about gravitation, which is a very interesting topic, not just from the course point of view, but also in general. Like, even if I told you you're not a major, still there's a lot of interesting stuff that can be done as a hobby as well. Okay. So, like I told you, and you don't need to know a lot of physics for pursuing such a hobby as well. It's fun activity that many people do, and there are a lot of sci-fi movies also based on these concepts. There are a lot of documentaries, there are a lot of videos, and then you can take it up at any level that you're interested in. Then I also introduced you to some work that has achieved Nobel Prize in this field, which is very interesting. I've also given and shared some information about this with you. So did you take a look at the information that I've shared with you guys? Okay, so can you see the book I'm sharing with you? So this is in the book, this is chapter number 13, gravitation, right? So as you know that we have now almost completed the course syllabus. So we have 2 more chapters to go. So one is this chapter number 13 that we are already doing. And the second is chapter number, just a moment, chapter number 13 and chapter number 15. These are the 2 chapters that we have to do now. So we were doing this chapter last time. We discussed a lot of stuff related to this, and we continue from there. So Newton's law of gravitation is one of the first laws that you must have become aware about when you came across this topic, even at school level, metric level, FSC level, O level, whatever you were studying. So it's a very simple law according to which every body attracts every other body with a force which is proportional to the masses of the two bodies, and it is inversely proportional to the square of the distance between the bodies. And then we also talked about the constant capital G, which is known as the gravitational constant. And this is G, capital G constant is different than the small g that we were studying in the previous chapters. Okay. So here you have the value of this gravitational constant. So if you're solving a problem and you need the value, this is the value. And again, like any other force, this is also a vector quantity. You can see the direction of this force is along the R vector, the unit vector R, which is shown here in the figure. So you can see two bodies, 1 and 2, and then they're having masses m1, m2, and then this is the force that's acting between them. So here you have an example of an apple which is on the surface of the earth, and you can see that the earth is pulling the apple and with a certain force, and you can see that this force can be calculated depending upon the mass of the apple. You can calculate the force, and as you're already aware that the units of force are Newton, of course, just like these are very basic things, right? You're already aware of them. So then we also talked about the principle of superposition and its application to gravitation. So superposition means that you're adding the forces that are acting on the particles, and then you are getting the net force. Just like we already have studied the concept of, the net effect on a body is equal to the sum of the effects on the individual particles, right? So when you sum the individual effects, right, you get the net effect. And in this case, this can be represented as a sum, but of course, a better way of writing this is to use the summation sign, which is a capital sigma sign, which denotes summation over the number of particles that are in your system. So in this case, if there are n particles, you start with these particles and you go up to n. And of course, if the number of particles is too large, then you can convert the summation sign into an integration sign, and you can find the value. So now, of course, the Earth is also a body, right? So the Earth has a mass which is usually represented by capital M. So in the last case, we were talking about M1 and M2, two bodies, and these were bodies having similar masses. But for example, if we consider the Earth, and we consider that the Earth is a very massive body, right? It has its mass is represented by capital M, and then we consider the gravitational force of a particle, which is a small particle as compared to the Earth itself. So let us say this is a particle somewhere here, and it has a mass small m. And in this case, capital M is much larger than small m. And the distance between these is r. Then the law that we had studied, which is F is equal to G m1 m2 over r squared, will be written as, instead of m1, we will write capital M, which is the mass of the Earth, multiplied by small m, which is the mass of the particle we are talking about, and r is the distance between these two, and therefore the formula becomes this. Again, we know that if the particle is released, if you have a particle a little bit above the surface of the Earth, you know that the Earth is a sphere. You can imagine the Earth to be like a ball, right? But it's massive, and it's much larger as compared to another particle that you may have above it. It may be a small particle like a ball or an apple or something. So if you know that if you hold a particle above the surface of the Earth and you leave it, what will happen? This particle will fall towards the Earth, right? So when it falls with a certain acceleration, which is known as the gravitational acceleration. Here it is represented by a G, okay, A with a subscript G. And then according to Newton's second law, we can write this F is equal to MAG, and MAG, AG can be calculated according to this formula by substituting in the equation above. And as altitude means the height, above the earth. So as the altitude changes, the value of this acceleration changes, okay? At, normally you can see that as it changes significantly, as the altitude changes significantly, this value changes, and it has been calculated for various distances. You can see that on the Earth's surface, we consider the altitude to be 0. And then the value of AG is 9.8 almost, right? And then as you start increasing the altitude, for example, Mount Everest is the highest mountain above the surface of the earth, the highest peak, right? And this is the altitude in this case is 8.8 kilometers. And in this case, the value of AG becomes equal to 9.8. It has been calculated to be 9.8. And then if, for example, you have these balloons that, people send up and above the surface of the earth. So as this altitude keeps increasing, this acceleration goes on decreasing. You can see that this is inversely proportional to the altitude. And if you're talking about a space shuttle, the altitude here is larger than, let's say, the mountain, and then the acceleration is less. And similarly, if you're talking about a satellite, then the distance again here is, this is the altitude, which is larger than the other distances we've been talking about. And then you see that the value of AG is less. So these are inversely proportional. They can be calculated for any case that you are given, right? Okay. So again, now you can have an idea of the formulas and how the values are calculated. So again, the Earth is a body where we know that the mass is not uniformly distributed, right? We know that the Earth is not exactly a sphere, although sometimes we consider it to be a sphere, but it's an ellipsoid. You know the shape ellipsoid. What is an ellipsoid? What is an ellipsoid? What's the difference between a sphere and an ellipsoid? Who would like to answer this? Yes, Hayan. What is the difference between a sphere and an ellipsoid?
Ma'am, ellipsoids.
Who would like to answer this? I'll give you a point.
Ma'am,
Yes, Arisha.
ma'am, a sphere is a proper circle, as in it's not bent, or it's not the radius is the same for all sides.
Okay.
Whereas in an ellipsoid, it's slightly pressed, yani ke the diameter of, if we take the diameter down the center, yani ke from the earth, if we take the diameter from the equator, then it's going to be larger than if we take the diameter from passing through the poles.
Good.
So that's an ellipsoid.
This was Arisha.
Yes, ma'am.
Good, Arisha. So a sphere is supposed to be perfectly round, and remember that this is, we wouldn't say this is a circle. You understand the difference between 2D and 3D, hai na? So 2D mein the shape is a circle, but actually these are 3D objects, and therefore it's called a sphere. You can imagine something similar to a ball, right? Let's say a football ball. And ellipsoid is again, the 2D version of the ellipsoid is called an ellipse, and then in 3D it's called an ellipsoid. You can imagine something like the egg, which is not perfectly round, right? You have one axis which is longer than the other axis, right? So something like this. Anyway, Arisha, that was good. Again, the earth is rotating. We know that the earth is always in motion. So that's another important fact about the earth. And you can see that you can again write such an equation for the earth, considering an example in which we have a box on the surface of the earth, and definitely there will be a normal force acting on this box, and then this will be balanced by the force given by Newton's law, and then when you subtract them, then this will give you the rotational velocity, and this will also depend on the radius of the Earth. So you can follow this, and this is the related force diagram where the normal force is upwards and the MAG is downwards, and therefore the box is being pulled downwards by a force which is given by MAG. So again, these are concepts that you have been doing previously as well, so they're not completely strange for you. So we can apply them in the context of gravitation and gravitational law of Newton, right? So again, potential energy is another concept that's related to gravitation, and in this case, we can assume that for particles which is on the surface of the Earth, right, it has a certain potential energy, okay? So for particles not on Earth's surface, the gravitational potential energy decreases when the separation between the particle and the Earth decreases. And so we have the symbol for gravitational potential energy is capital U, and the gravitational potential energy is assumed to be zero for when the body is at an infinite distance from the Earth. So for R is equal to infinity, U is equal to 0. And as the R decreases, the value of U also decreases because we have a negative sign in this formula, and according to this you can calculate the gravitational potential energy. The signs are a convention, just like, you know, previously we were also studying the signs, like we took counterclockwise to be positive and clockwise to be negative. Similarly, we have assumed some sign conventions in this case as well. So you can apply these sign conventions and you can calculate the gravitational potential energy. And if you have more than two particles, for example, you have three particles, M1, M2, M3, all of these particles will exert a certain force upon the other particles. So you calculate the force in pairs, and then the total gravitational potential energy will be a sum of each pair's gravitational potential energy. So you can sum them like this, and this will become the total gravitational potential energy. So here you can see the example of the Earth and a bat, a baseball bat, for example, and you can see that the bat is being pulled towards the Earth with a force which is capital F. And there are some properties of this force. This force does not depend upon path, and you can see this from here. Also, the potential energy and force can be related by this formula. Escape speed is another concept that's related to this. So are you familiar with escape speed? Have you heard of escape speed before? So we did study projectiles. You remember in one of the last chapters, we also performed practicals on projectiles. So whenever you fire a projectile upwards, okay, so it will slow, it will stop, and then it will return to the Earth. So that's the usual behavior of a projectile, okay? As you already know, you've performed it, you've studied it, you've made many calculations for problems related to this, right? So, however, there is a certain minimum initial speed that will cause it to move upward forever. So if there's a minimum speed, if the speed is above that, the projectile will not return to the Earth, rather it will start rotating around the Earth, and this is called the escape speed, okay? So the escape speed can be calculated, and this is the formula for the escape speed. So this formula can be used to find the escape speed of a projectile from any astronomical body. We're using the Earth as an example most of the time, but it can be used for any other astronomical body as well. And here you have some examples of escape speeds, but you can see that these are large speeds. I mean large radii of the bodies, because these are astronomical bodies. Okay, now let's look at a problem related to the concepts that we have discussed, and let's apply those concepts to solve a problem. So let's look at this one. We have a figure in which we have an arrangement of three particles. We have mass M1, we have mass M2, we have mass M3. So we have three particles, 1, 2, and 3, having the masses M1, M2, and M3. M1 is given to be 6 kg, M2 and M3 are equal and each is equal to 4 kg. Now the distance between M1 and M2 is A, and the distance between M1 and M3 is 2A. So the question is, what is the net gravitational force on particle 1 due to the other particles? So M1 experiences a force due to M2, and this is given by the vector F1, 2. Similarly, M1 experiences a force due to M3, and this is given by the vector F1, 3. Also, you can see that the direction of the forces are along the R vector for each case, as we saw when we were explaining this. Okay, now the formula we know is given by F is equal to G M1 M2 over R squared. But again, remember that we will use this formula first for one pair of particles, and then we will use this formula for the second pair of particles, right? So for the first pair, let us consider the two masses M1 and M2, and the force for this case would be F12. So instead of F, we will write F12, and then we write the masses M1, M2, and then instead of R, we are writing the distance between the two masses M1 and M2. And this distance we can see is given, the value is given as 0.02 meters, right? So substituting all these values, G is a constant and we have the value. Substituting all these values, we find that F12 is equal to 4 into 10 raised to minus 6 newtons. Now, just like we calculate F12, we can again apply the same formula for the other pair of particles, which is 1 and 3. So the formula is the same, but now instead of M2, you have M3. The rest, and instead of R, the distance has also changed. Previously, the distance was A, now the distance is 2A. So we substitute these values, and you can find the value of F13 here. So F13 is equal to, has been calculated 1 into 10 raised to minus 6 Newton. Again, you can, since these are vector quantities, you can see the directions of these forces according to this diagram. You can see the horizontal axis is the x-axis, the vertical axis is the y-axis, and then F12 is along the vertical axis, the positive y-axis. You know, if you go from the origin, if you take the origin here, then going upwards is the positive y-axis, and similarly going towards the left is the negative x-axis, going towards the right is the positive x-axis, right? So keeping these directions in mind, we can understand these. So in this case, F13 is a negative direction vector, so we have a negative sign with this. F12 is in the positive y direction, so it remains positive. Now again, from chapter number 2, you remember vector addition and Pythagoras theorem, you know, and in that case, if you have the vertical rectangular components, this is like a triangle, you can form a triangle here, right? This becomes a triangle, a right angled triangle, and this is, you can see you have the sides of the triangle, right? We call this the adjacent side, we call this the opposite side, and we call this the hypotenuse, or you can call this the base and the perpendicular and the hypotenuse. And you know that when you take the square of these two, the sum is equal to the square of the hypotenuse. So using that formula, we can put in the values that we have calculated for these, and we can find the net force, which comes out to be 4 into 10 raised to minus 6 newtons. Again, when we are dealing with vector quantities, we have to calculate the magnitude, and we also have to calculate the direction. And in order to calculate the direction, we need we can use the trigonometric ratios, right? So according to the trigonometric ratios, we can use the tangent ratio. Tan theta is equal to opposite side over adjacent side. So opposite side in this case is F12 divided by F minus F13 because it's in the negative direction. And then we take the tangent inverse and we calculate it, and this is the answer we get. Now I will stop here and I would like someone to explain to me if we can use this as an answer. Can we use this as an answer? The person who will explain this, I will give you a point for this. So we had a similar case in a previous chapter also when we were calculating the sine of an angle. And again, this was something I explained in class, and I would now like someone to explain this. Who would explain this angle and how we can go about it? पहली बात बताओ, can we use this value as the correct value? Hello?
मैम एंगल नेगेटिव में है तो इसको मे बी ना
कौन बोल रहा है?
मैम हयान।
हयान, नेगेटिव है तो क्या हुआ? नेगेटिव, हाँ बोलो आगे। यस, नेगेटिव है फिर? यस
मैम इसको पॉजिटिव में कर सकते हैं हम लोग।
क्यों करें पॉजिटिव? क्या
मैम
प्रॉब्लम है?
डायरेक्शन-
नेगेटिव में
मैम
क्या
डायरेक्शन
प्रॉब्लम है?
मैम अगर डायरेक्शन हम उसके अंदर पॉजिटिव के अंदर कर दें जब नेगेटिव के अंदर जा रहे हैं एज फ्रॉम ग्राफ।
नहीं, दोबारा बोलो, मुझे इट्स नॉट क्लियर व्हाट यू आर सेइंग। दोबारा बोलो।
मैम ग्राफ में हम नेगेटिव की तरफ से हम वैल्यू ले रहे हैं ना उसकी, तो मैम अगर वहाँ पे आंसर अगर हम लोग इसके अंदर -76 ले रहे हैं मैम, वो हम पॉजिटिव में भी तो कन्वर्ट कर सकते हैं।
पॉजिटिव में भी कर सकते हैं, लेकिन क्यों करें? व्हाई?
मैम क्योंकि इसकी जो वैल्यूज वो कह रहे हैं मैम, वो पॉजिटिव इसके अंदर करना है क्योंकि एज इन क्वेश्चन भी स्टेटमेंट।
अच्छा, विल समवन एल्स एक्सप्लेन दिस? कोई और बताएगा? Who would like to try? Yes? Who would like to explain this? अच्छा, आप लोगों को याद है we had a similar issue in one of the previous chapters again, and in that case I referred you to a formula. These formulas are known as trigonometric identities. Okay, so sometimes you can use your calculator and you get a value, but you also have to see that that value should also make sense physically. So if we talk about -76 degrees, it means it's in this direction somewhere here. -76 will be here. So you should make physical sense of this, and if it's you think it makes sense, it's fine, you can accept the answer. If not, then you can apply one of the trigonometric answers, because the same tangent value or the same trigonometric value can exist for more than one angles, but there are specific formulas for this. The last time we were doing it for sine. Okay, so this time we're doing it for tan or tangent, right? So you can see that these are called quadrants. So this is quadrant 1, and this is quadrant 2, this is quadrant 3, and this is quadrant 4. So from the physical description of the problem, we can see also from the force diagram that this in which quadrant should the force be? The final force should be in which quadrant? किसमें होनी चाहिए? 1, 2, 3 and 4 कहाँ पे होनी चाहिए? Who would answer this?
मैम 4 में।
4 में होनी चाहिए। कौन बोल रहा है?
मैम हयान।
हयान, अच्छा, हयान thinks that it should be in the 4th quadrant. Would anyone else like to try?
Ma'am, can you repeat the question?
बेटा, कौन से क्वाड्रेंट में जो हमने नेट फोर्स कैलकुलेट की है? अकॉर्डिंग टू दिस डायग्राम वी हैव कैलकुलेटेड द नेट force, right? In which quadrant do you think it should be? Like I've marked the quadrants, right? 1, 2.
Ma'am, second quadrant.
It should be in the second quadrant. Who is speaking?
Hamza Dar.
Hamza Dar. Okay, good. Why do you think it should be second quadrant? Means it should be somewhere here. Hamza Dar, why do you think it should be in the second quadrant?
Ma'am, because it does not make sense if it lies in other three quadrants.
Okay, very good. You're right, because we can see that the forces are here, so the resultant should be somewhere between, somewhere within the second quadrant. यहाँ हो सकते हैं, इसका resultant यहाँ तो नहीं ना हो सकता according to this diagram that we have. Okay, and again you can go to chapter 3 and look at this. To understand it, and also you know that the angles in the quadrants, quadrant 1 is between 0 degrees and 90 degrees, hai na? So quadrant 2 is between 90 degrees and 180 degrees. Quadrant 3 is between 180 degrees and 270 degrees, and quadrant 4 is between 270 degrees and 360 degrees, right? So if we, like we just explained, it should be in the second quadrant. If it is in the second quadrant, the answer of the angle should be between 90 and 180 degrees. It's not minus 76. Minus 76 falls in the fourth quadrant, which does not make sense according to the diagram and the description of the problem. So in the second quadrant, it should be somewhere between 90 and 180 degrees. So for this purpose, like I said, that when you calculate tangent values or trigonometric values, you can have two angles having the same trigonometric values, and these are called trigonometric identities. These are formulas. Okay, so according to that formula, minus 76, and there's another angle also that will have the same value. And you can again go to chapter 3 and look at this tactic 3. There you have an explanation of this, and you can see that the tangent of an angle theta is the same as the tangent of 180 degree plus that angle theta. So if you use that trigonometric formula or that trigonometric identity, then you can find the second value of the angle that corresponds to the same value in this equation, and that answer comes out to be 104 degrees, and 104 degrees is between 90 and 180 degrees, so therefore it is in the second quadrant. And then this physically makes sense. Both these answers are correct mathematically, but physically only 104 is possible, so we will select 104 as the correct answer. And there are identities formulas for this, and I have also uploaded a link where you can see an explanation of these identities if you're interested. So I'm just going to share something with you right now. You can see it. I've also shared this on Moodle. So tan theta plus pi is equal to tan theta. So tan theta plus pi means tan theta plus 180 degrees is equal to tan theta itself, and using that formula we've been able to find this. This is explained in chapter 3. It's also explained in the link that I have shared with you. I am going to show you shortly this this video, and you can also go and see this again from Moodle that I've shared with you. So I'm going to share it here, right? So this is the video that I've shared with you here. This is about
in the previous video, we explored how the cosine...
Can you see the video? Can you guys see the video? I cannot hear you.
Yes, ma'am.
Yes. Okay. So please, this video has also been, the link has been uploaded to Moodle. You can go and watch it there as well. But the formula that we just used in this case is also given in this video. It's also given in many mathematics books. So it's a simple trigonometric formula. So you can see that the sine values, there are some angles where they are equal. So for tangent
Sine and sines of angles relate when we are setting
let's
angles.
look at the tangent
of the terminal rate in theta. Well, we're tangent x. But what other angle? The tangent of theta. Let's see if this actually is the case. these two things should be equal. If we
Okay, the formula that we just used is tan theta plus pi is equal to tan theta. Okay, so where pi is 180 degrees. So this is the formula that we used. Last time we used a formula for sine in chapter number 3, and this time we're using a formula for tan. So this is an explanation of how we got that formula. So you can watch this. You can also go and look in chapter number 3 and you can see the explanation for this. So I'm going to take the attendance now. And in this case, let's see who's present. So Sarmad, Amar, Abu Bakr. Abu Bakr did join for a short time. I think he's not here right now. Okay. Fatima Babar, no. Usman Bajwa, yes. Usman
Yes,
Bajwa.
ma'am. Yes.
Okay. Anam Basharat, Muhammad Bilal.
Yes, ma'am.
Yes, ma'am.
फरीदुद्दीन. हमजा डार ने फिर सही कहा था ना आंसर, सो हमजा डार गेट्स अ पॉइंट. ओके. एंड और किसने आज एक क्वेश्चन आंसर किया था शुरू में? एलिप्स वाला क्वेश्चन किसने आंसर किया था? अरीशा ने.
मैम मैंने, अरीशा ने.
हाँ, अरीशा का. अरीशा कहाँ है? दिस इज अरीशा. यस, ठीक. ओके. Fariduddin is not here. Kessler is not here. Zarish?
Yes, ma'am.
Okay. Haris is not here. Muaz?
Yes, ma'am.
Okay. And Hafiz Ibrahim is not here. Humayr Shad is not here. Alina?
Present, ma'am.
Okay. Hunain? Hunain is not here. Rana Shahbaz is not here. Sania Ahmed is not here. Arisha is here. Arisha? Chand Khushi?
Present, ma'am. Arisha.
Good. Chand Khushi? Maiza? Maiza is not here. Yusuf Patras is not here. Abira? Abira?
Present, ma'am.
Yes. Nadia Mukhtar is not here. Hayyan?
Yes, ma'am.
Okay. Cheryl is...
Present, ma'am.
Okay. Ashraf? No. Huda Zahur? No. Amelia? Amelia, are you there? Bisma? No. Sadiqullah? No. Tahir Sohaib?
मैम सोहेब ताहिर.
Yes. Amelia?
मैम मीटिंग दोबारा ज्वाइन करनी है?